Okay, so welcome to EE306001 Probability class. Chapter 1, I ask you to self-study the material, and we have held the first quiz last night. So today I will start with chapter 2. It's on the axioms of probability. So, okay, I believe that you have touched the subject of probability in high school, and I think that at that time you learned probability from a kind of intuitive way of thinking, and but in this semester we will actually developed the framework of the theory of probability in this chapter. And of course, I will try my best to illustrate some of the examples to examine the spirit or the basic principles of all the axioms proposed in this framework. Okay, and so if you have any questions, just stop me in the lecture time. Don't hesitate to do so. I know. In my time, that back to 40 years ago, I was very shy, so I'm afraid of raise my hand. But when I was a graduate student, I actually I think that it is not a big deal to raise your hands, because that the cost to raise your hand compared with the question you left and back home to think about it, compared with the time you will spend, you will see that to ask a question in time is very effective and save you a lot of time. Okay. So let me know if you have any questions. All right. All right. So I will start with. So basically, I will follow the textbook, and I ask you to read the textbook carefully. Personally, I love this textbook, and there are a lot of examples, and so it will give you a comprehension of the whole subject. All right. Okay, so the first one is about the sample space and the event. Okay, so basically, probability theory deals with a physical system, but with random phenomenon. So we call that as a physical random experiment. Okay, and a physical random experiment corresponds to a mathematical model. Okay, so we'll talk about and we'll illustrate some of the physical random experiments and to show how do we develop a mathematical model to describe this random experiment, and so that we can investigate and to answer some of the questions raised from this random experiment. Okay, so let's take an example. All right, so the vertical random experiment we considered it is a race among 5 horses. So we named the horses as A, B, C, D, E. Okay, so we have 5 horses, and we hold a race among them. All right, so that is the physical random experiment. And then you may think about that as you have seen a lot of movies that some people try to control, right? To control the game or the race, because there are a lot of people gamble a lot of money on the race. But suppose we are facing with a fair game, that without any control, any manipulation. Okay, so in a race, and all the horses will be in good conditions. I mean, apparently in good conditions. So the competition sometimes depends on a lot of factors, including the riders, all right, the riders, and also the road conditions, maybe the health conditions, some variations on the horses. Okay, so the outcome sometimes actually is random. Otherwise, if it's not random, as you can see, if people can project or can guess the results in a very high, or you can say definitely, what is the result? It will not have any gambling, right? Why? Because because everybody will make money, and the game will broken quickly. Okay, so you can see a race should be random. The result should be random, so that's the odd can be positive or negative. Okay, and a fair game is that the expected game should be 0. Okay, so that just like a casino. So anyway, so to model such a random experiment, just the horse racing, so that let's see what kind of mathematical model can we build. All right. So first of all, we will see the possible outcome. Okay, the possible outcomes in such a race. Okay, so the result will be all 5 factorial permutations of A, B, C, D, E. Okay. Permutation is a terminology you have to know when you study the combinatorial analysis. Okay. Right. So that's why I ask you to self-study chapter number 1. Otherwise, when I talk about all these terminologies, I have to explain that terminology. So they are factorial permutations. Okay. So we have so that is 120 outcomes. Okay. So we have 120 outcomes of the result. Okay, and so the set we call S of all possible outcomes well, it's called the sample space. Okay, so we call it, and so in set theory notation would be the all 5 factorial permutations of A, B, C, D, E. Of course, you can enumerate these 120 outcomes. Okay, one way is that say A, B, C, D, E. So by convention, A is the first, B is the second, C is third, D is the fourth, and E is the last. The other is C, A, B, D, E, and etc. Okay, so you can express this set by enumeration, okay, but it will take some time to complete it, right? So allow me to just write it in this way. So a full description will be this way. Okay, so there are many different ways to describe this set. All right, and this set is called the sample space. Okay, of the random experiment. All right, now we particularly ask for events. Right? So for example, example 1, host A, right, is the farthest. Okay? So that is an event. Okay, so if a gambler bet a lot of money on host A, then the return will be a lot, right? And so the host A is the first, right? So that is an event. The second possible event is B is faster than C, all right? So host B is faster than host C. Okay. The third event would be E is the last. Okay. Another would be B is the first. Okay, and then D, then C, then E, and A, the last. Okay. Okay, so you have a lot of events to describe. All right, so that they are all possible events. Possible event to happen in such a horse race. Now, mathematically, so they are verbal description, right? And in mathematical notation, we will say that each event, okay, can be represented by a subset of the sample space. Okay, so let's see how do we describe all these events by subsets of the sample space. Okay, so host A is the farthest. Okay, so now, we call event number 1, E1. So E1 will be, because A is the farthest, so you can say A, B, C, D, E, A, maybe it's D, C, B, E, Okay, a lot of things. Okay. Say A, E, and D, and C and B. Okay. Right. So the point is that A should be placed in the first place. Okay, because A is the fastest. Okay. And from here, we know that this is say with the size E1. So the size of a say usually denoted as the absolute value of E1. Okay, that is a mathematical notation, right? And why is that? From your knowledge, you know this is 4 factorial. The reason is that except the first place, the other 4 places can be arbitrary, right? Okay, so B, C, D, E can be arranged arbitrarily. So that would be a permutation of B, C, D, E. Okay, so the size would be 4 factorial. How about the second event? B is faster than C. Okay, so we call this is E2. Right, a typical example, because B is faster than C, right? So it's possible that B, C, right? So that these 3 prices can be placed arbitrarily, or you can have, say, okay, there are a lot of possibilities. The only requirement is that B should be placed right left to C, because B is faster than that. Okay, and we know the size of E2 is what? Sub E2 is that first of all, from the 5 positions, you choose 2 positions to place B and C. Okay, right? And and B always before C. Okay, so there is only one possibility if you choose 2 places. And the rest of 3 places can be arbitrary arrangement of A, D, and E, right? So that this is chance 3 factorial. Questions? Okay, no question, good. Now, event 3. E is the last, so that is right. So that the first 4 places can be arbitrary among A, B, C, D. Okay, and so that the size of E3 is 4 factorial, right? And the 4, the E4, all right? So you can see the result, the outcome, there is only one possible outcome because the order has been determined, the B and the D and the C and the E and the A. Okay? So the size of E4 is 1. Okay. Questions? Right? So all of the descriptions, when you say that you can always represent each event by a subset of S. Okay. All right, and so an event E is said to occur, okay, if the outcome omega of the random experiment is in E. Okay, so that is the terminology. When we say an event occurs. All right, so now, for example, suppose the outcome, all right, so suppose the outcome omega is equal to okay, so suppose the outcome of the horse race is this one. This is the outcome. Now, so we say that, from that we see, does event A, event E1 occur? Well, yes. So because A is the fastest. Then event E1 occurs. All right? How about event E2? E2 says that B is faster than C. Okay? So B is faster than C, right? Okay, so event 2 occurs. 2. But how about event 3? E is the last? No, right? Because this one is not in E, E3. Why? Because the outcome in E3, then E must be in the last place here. So that E3 does not occur. All right, how about 4? Right? E4 is this E, B, D, C, E, A. Apparently, this outcome is not in here. Okay? And then neither. E4. Okay? Now, it's usually a main task, okay, to determine the probability that a specific event occurs. Okay, so this is the probability that a specific event occurs. So for a gambler, I think event number 1, because if he or she would like to bet on horse A, then he should estimate or should know the probability that event 1 to occur, right? Because if event 1 occur, then the bet is successful and he will win a lot of money. Okay, so the gambler should calculate the probability of event number 1, for example. Okay, and so if the probability is low, okay, if the probability is low, then of course the probability is low. Then the gambler knows, and also I think the company is also, the gambling company will also know that. And so, as you know, if the probability is low, then the return will be high. Okay, because risk is high too. Okay, so that for the business of gambling, to do this task is very important. Okay, very, very important. So how do we calculate? How do we determine the probability of a specific event? How? All right. So, and we will describe the way to do so in the next subsection. Okay, but before that, I want to deal with the event more. So, for example, events connected, okay, or operated by logical operators. So what kind of logical operator we will have? Well, usually like AND, OR, and NOT. Right? So AND, OR, NOT, there are 3 common logical operators. Okay? And so events connected or operated by logical operators are event 2. Okay? So for example, the event that A is the fastest and E is the last. Okay? All right, so A is the fastest and E is the last. It's this event E5. Okay? So it's AND, right? So to be the AND, then, so that means that the E1, A, because E1 corresponding to event host A is the fastest. And intersect with E2. And E2, B, E is the last, I'm sorry, E3. Okay. Why? Because that in this way, we have A. So the event 5 should be this event. It can be represented by a subset, right? And it should be A should be in the first place, E is the last place, and so you have B, C, D can be arranged arbitrarily. Okay. Okay. So the AND, the logical operation for 2 events corresponding to the intersection Okay, because intersect means that so E5, the size of E5 is 3 factorial. Okay. Okay. Right. So event can be connected. And the logical operator AND corresponding to intersection in set theory notation. Okay. Okay. All right. And so that there are a lot of events. So the collection of all events of interest, okay, will be denoted by a mathematical script notation F, okay. So that the collection of all events of interest. Okay, I will explain what do we mean events of interest in third of interest. Because you can choose event of interest as you wish. But when you choose event of interest into a collection, we say that F here, some mathematical structure should be fulfilled, and I will talk about that later. All right, so the collection of all events of interest will be denoted by F. Now, in this example of horse race, okay, so in this example of horse race, F is the power set of S. What is the power set of S? Okay, some of you may know that. It is the collection of all subsets of S. Okay? So that it include the empty set, the subspace itself, or a singleton, just only a member. All right? A lot, okay? So the collection of all subset of the sample space is called the power set of the set X, okay? So this is a terminology in set theory. And what is the size? In this case, it's still a finite set. So what is the size of this collection? Because in this collection, each member is a subset of the sample space. So what is the size? Okay, the size. This is the number 2 to the size of S. And in this case, so we have 32 only. Oh, no, sorry. So it's a huge number, I'm sorry. A very big set. Yes, please. Mm-hmm. No. A is an element of the sample space. So the sample, oh yes, I'm sorry, you are correct. So that's why, yeah, I'm sorry, you are correct. This number is correct, but this is not correct. I should say A. Yes, yeah, I'm sorry. You are true. Yes, a lot, I'm sorry, yes. Thank you for the correction. Yeah. Okay, so this is a very big number because that is approximately it's a very big number, right? It's 10 to the 36 power. Okay, so this is so that so possible event is amazing, right? This is a very simple example, but you can see in this case because every event can be described by a subset of the sample space. Okay, the sample space contains 120 possible outcomes. Okay, and so that so the subset, the number of possible subset will be such a huge number in here. Okay, and so there are such huge number of possible events to occur. Okay? Occurs. So that's why it's a very good business. Why? Because you can see the event. This is a huge number of events. Okay? And the host, we have only 5 hosts only, right? But in many situations, you can see that especially when I saw a movie from Hong Kong, that at least some of them, they may have 8 to 10 horses to race. Okay, and so the number will be much bigger than this number. Okay, so even for this simple random experiment, the variety of the possible events you can look for, it's a huge number. But this is a huge number. Okay. And when you think about the random events from the nature, then you can see that that would be quite small, right? Compared with the random phenomena occurred in the nature. Okay. All right. Okay. So any questions? Okay. All right. So now, all right. All right. So let me consider another running experiments with different nature. Okay. Physical random experiment. It's measuring the lifetime of a light bulb in working hours. Okay. Do you want to measure light bulb in working hours? Working hours means that you turn on the light, and then you measure the lifetime of the light bulb. All right, so let me see the mathematical model. Well, even though the modern company who manufacture light bulb try to have a very good quality control. The good quality control has a goal. For example, when you look at the specification, when you buy a light bulb, okay, so you can look at the specification. And the specification always say that the light bulb is guaranteed to have a lifetime, for example, that 6,000 hours. 60,000 hours. Okay, so that is the specification. So it guarantees that when you buy this light bulb, the working hours for this bulb will be at least 6,000 hours. And but you can have the intuition say that well, not every light bulb can have a light bulb, okay, always greater than or equal to 6,000 hours to work. But very few people, right, do the experiments. Why? To record the working hours of the light bulbs, right? So some of them may have the working hours less than 6,000, right? But the company, the manufacturing company, try to make this percentage to be small. For example, maybe 0.1%, maybe that, so that you will try. Okay, and so you may think about, well, to have to safeguard the specification, then the manufacturing company may have to decide a policy that, well, maybe internally try to raise the standard, right? Even though the specification says 6,000 hours, the company may say, well, maybe we can manufacture that bulb with the lifetime hours for 10,000. That would be very good, right? 10,000 hours, so that the probability that a light bulb of customer will buy a bulb so that the lifetime of light bulb will be less than 6,000 hours. The probability will be 10 to the, for example, 10 to the minus 10. This probability is very low, almost zero, right? So the company will say, wow, we are very proud that our quality, the specification says 6,000 hours, we guarantee 100%. That's when you buy our light bulb, the guarantee would be 100%. But that's a good thing, right, for the customer. But for the manufacturer, to raise the standard such high, the investment, the material will have a high cost. All right, so the earning will be low. Right, you can see. And so the best strategy for the company would be that if we have a quality control manufacturing line, then we will make sure every light bulb have the lifetime to be just 6,000 hours. Exactly, no more and no less. Okay? And it's possible. Okay, so that is because if the exactly 6,000 hours, customer was satisfied because the specification says 6 hours, 6,000 hours, and the company will earn a lot of money. Why? Because just this point, just fulfill the guarantee, and no more cost, then should be paid. Okay. Okay. So that the company will should be to answer the question: is that possible? Okay. So in terms of probabilities, that what is the probability? What is the probability that a light bulb to have lifetime exactly equal to 6,000 hours? What is that probability? All right? And I believe you will know the answer after sometimes later in this semester. Okay? All right, so let's see. To deal with that, we should prepare for a mathematical model, right, to answer that particular question. Okay, so first of all, we have to say possible outcomes. The possible outcome should be non-negative real numbers. Okay? Because lifetime, in the extreme case, the lifetime is 0, means that when you turn on the light bulb, you burn out immediately. Okay, it's possible, right? Okay, so that's negative real numbers, and so the sample space is, and the lifetime can be very long. It's possible, right? In principle. So the sample space is equal to the R plus. R plus is a mathematical notation for this interval, starting from 0 to infinity. Okay? So the sample space is this set. And this set is infinite set. Okay? It's not like this one. This set is a finite set because it has only 120 possible outcomes. But the sample space here, the set is infinite. And it is also uncountable. You cannot count it. Okay? So that so this is an uncountable infinite set. Okay? Uncountable. You cannot count all non-negative real numbers. You can't. You cannot count it. So it's called uncountable. All right, and possible events. Okay? What kind of possible event we raise up? One is the bulb is broken after 1,000 hours. The second one, we have to replace the bulb during the 500th hour. Okay? And third one, the bulb is broken just at the moment of 6,000 hours. 6,000 hours. Okay, again, we will describe so that event number 1 So event number 1 would be okay. Contain all the possible outcomes. The outcome so that is broken after 1,000 hours. Okay. Okay. Because E1 is an infinite set, so it's impossible to enumerate all the possible outcomes in this event. Okay, so is that a subset of X such that the outcome now is the left term, right? So the left term is greater than 1,000 hours. Okay, so this is subset. So you see that this is a subset of the S. Any questions? Okay, now E2, we have to replace the Bob during the 500th hour. So it's the subset of the summer space such that before okay, so that is in between 499 and 500 because this is in the 500th hour. Okay, again, it's a subset. How about E3? Exactly broken, right? At the moment of the 6,000 hours. So that would be 6,000. And this is just 6,000. Of course, it's a subset of the sum of space. Any questions? So now we consider some events connected or operated by logical operators such as and, or, and not. Event 2, right? We know that they are all event 2. So for example, the event that the bulb is not broken after 1,000 hours. Okay? So the event is this event, E4. And the E4, so E4 is the complement. Because not means complement in set theory. The complement of the E1. Because E1 says that the bulb is broken after 1,000 hours. But this event is that this bulb is not broken after 1,000 hours. So E4 is the complement of E1. And what is that? So this is such that okay, so it's this set. And so this is the sample space. Maybe I will write it down here. So the complement of E1 actually is the difference set. The set X by the minus the E1. Okay? And so that would be okay. All right. Now in this example, okay, the collection of all events of interest is not equal to the power set of the sample space. It's not. Okay, in this example. All right, for several technical reasons which we will not address here. However, it is demanded that, okay, so it's demanded that, so to have a collection of all events of interest, we will have that one, all intervals of R plus must be in the collection. F. So you can see that E1, what is E1? Actually, this is equal to, in terms of interval, this is equal to, okay, right? In terms of if E2 is equal to, okay, so it's a open half-closed interval. This is the open interval. And why is that? This is just a point only. Okay, so this point, this one is equal to, okay, it's a closed interval. Okay, so a special type of, okay, and the complement, this is equal to 0. So this quite often we describe outcome. So the thing is the outcome is a value, is a continuous value. Okay, so the nature is quite different from the horse race, because the problem of horse race is discrete. Okay, they are discrete things, but we are talking about lifetime, which is continuous variables. Okay, this is continuous numbers there, and so usually use an interval to describe an event. Events, okay, many events of interest can be represented by an interval. Okay, by an interval. So So that so we require all intervals of R plus must be in the collection F of events of interest. Okay, so we will select intervals to be events of interest. The second requirement is that if E is in the collection F, then E complement is also in the collection of event of interest. Because not, right, is the logical operation. So if E is an event of interest, we ask that the not of E should be also an event of interest. The last one, countable unions or intersections of events in this collection F must also be in F. Okay? Because when we like the countable, because later on we ask for the countable union, because we ask for countable many events to connect by using the or and. Okay? So we want countable union or intersection of events in F must be also in F. Okay, so we require the three requirements here. Okay, so the first one is very practical because as we illustrate here, many events can be described by intervals of this set. And the number 2 and number 3 are logical reasons, right? Logical reason, because if E is event of interest, then the not E should be also event of interest. And also the union and or should be after the connection by using and or, then there must be events in F2. Okay, so of these things together, right? They are all strict requirements. So running experiments like this one has a nature quite different from the running experiments we have done for the horse race. Okay, but we will investigate both of them later. Okay, all right. So let's take a rest here up to 2:20. Okay. Okay, so let's go back to our discussion. Right now, we talk about from the above two examples. We know we have to identify events of interest, all right, and put them together as a collection. Okay, and so if we want to establish such a collection of events of interest, you have to satisfy some so-called logical reasoning, right? You have to do with the logical reasoning. Okay, and so this list, so the collection we call F of events of interest is required to satisfy. Okay, so that is the minimum requirement for us to have a logical reasoning. So the first O is that the sample space itself is an event, must be an event in F. So we will ask the sample space S to be an event of interest. All right, and S is usually called the total event. Why? Because that this total event must occur. Because it is the set of all possible outcomes, right? So when you do the experiment, no matter what kind of outcome you have, the total event will occur. That is reasonable, right? Okay, and fulfill our intuitive concept. Okay, so the sample space S is an event, and we call it the total event. The second requirement is that if E is an event in F, says that if E will be put into an event of interest, then we ask not E, or the complement of E, defined to be, is also an event in F. Okay? Third one, if E1, E2, are events in F, then E1 union E2 union is also an event in F. Okay? All right, so a collection F of subset of the sample space S, which satisfy the above three properties, is called a sigma algebra, our sigma field. Okay? And the members of a sigma algebra F, the members of X are called events of interest. Or called measurable, say. Okay. Measurable set means that later on, we will assign probability on events of interest only. If any subset of the subspace is not included into the sigma algebra, then it is not measurable, and then we cannot assign probability on it. That means that we will not investigate this kind of so-called event because it's not event of interest. So in the examples of horse race, it is intuitive to have F equal to the power set of the subspace. Okay? Okay. But if we limit ourselves to a smaller sigma algebra, says for example, G and okay. So if we consider this smaller collection of subset of the sample space is. All right, by requirement 1, the sample space should be in a sigma algebra. So this is fulfilled. First requirement is fulfilled. How about the second requirement? Well, because the empty set is in G, now the complement of the empty set is S, right? So S is in G. No problem. S is in G. S, the complement of S is the empty set, so it's in G. Good. Now, this is a singleton. A singleton means that a subset contains only one element. Okay? So this is called a singleton. Okay? All right, so this is in G, and its complement is this one. So it's also in here. And the complement of this subset is this one, because they are complement to each other. Okay, so the second requirement is fulfilled. How about the third requirement? Well, in here, we ask for countable many events, then the union would be in F. But we have only 4 events. So the union of this and that, S union with this one is equal to S. This is said, this event, union with this event is equal to the total event. So you can see that any union is also in the G. Okay, so this is a sigma algebra. Right? Now, if you take G as the collection of events of interest, then only this event and its complement and also the total event can be investigated and assign the probability on it. So that event like the host A is the fastest, cannot be investigated because this event is not in G. So host A is the fastest is not an event of interest for you if you decide to select G as the sigma algebra for further study. Okay? And you can see you have many other possible choices of sigma algebra because any collection of subset of the summer space satisfying 1 to 3 would be called a sigma algebra, would be called the collection of events of interest. When you model your running experiment. Okay? And of course, you know, you will abandon this choice and go back to this choice. Okay? Go back to this choice. There. Any questions? So this is 3 requirements. Is the the bottom line for a collection of events of interest to exist. That is the bottom line. And this is because for the logical reasoning. Okay? Later on, we will have and and or and not all these logical operations to work on the events. Okay? So to solve your random experiments, you have to select a proper sigma algebra. Okay, it's up to your decision. Okay, different decision will answer different scope of questions. Right? So you have to choose a proper one. And for discrete problems like horse races, the policy of the sample space is usually a proper selection, except some exceptional case. I mean, in some special cases, you don't need to use the policy, okay, for discrete problems. But for continuous problems like a lifetime of light bulb, as I mentioned before, to select the policy of the sample space is not a wise choice for some technical reasons. But I think I have no time to talk about that. But usually you can see here the 2 and 3, right? Corresponding 2 and 3 here. And also the intersection, I will prove that later on. All right? Because in 1, 2, 3, we talk about unions only, right? But we will talk about intersection soon. Okay. And the additional requirement for the study of the lifetime of light bulb is that we ask that all intervals of the sample space must be events of interest. Okay? Because as we illustrate, a lot of events, sensible events, okay, which you want to study, you want to investigate the probability that this event occur, is that they are intervals of the sample spaces. Okay, so this is additional requirement, right, to that. So this is the baseline. This is the baseline we should have. All right, and so first of all, I will demonstrate the first lemma about the De Morgan's law. The De Morgan's law says that let En be a collection of subset of a set. Okay, so arbitrary. So this is a collection of subset of a set. Then you consider the union of En. Okay, so you take a union and you take the complement. So what is that? Then this is equal to the intersection of the complement of each En. Okay, and if you take the intersection first, okay, of En first, and then take the complement later, then this is equal to you take the union of the complement of individual UN. All right, so this result are called De Morgan's law. Okay. Okay, and the proof, right? So an element is in the union okay? If an only is not in okay? So if only if X is not in En for all n from 1 to 3. Okay, so that means that X is in En complement for n 1, 2, 3, etc. And so that means that X is in the intersection. Okay, and we have done. So let me know which steps you have question. The other one, complement, that means that X is not in this intersection. Okay. So this means that at least one such that X is not in En. Okay, so that means at least one such that X is in the complement. And because at least the one, so that is the union of so that is in the union, at least, right? For all means intersection. At least it's or. Okay. So it's called the De Morgan's law. And a remark. The De Morgan's law are valid for a general collection EI of subset of a set where I can be any index set. All right, finite or countably or uncountably infinite. So in this version, it means that the union of I in the index set EI take the complement is equal to the intersection I in index set is equal to the union and the proofs would be the same. Okay. In here, we use countable infinite set because the index set I is just the set of all positive integers, the n, right? Because the index is from 1, 2, 3, 4, 5, 6, 7, 8. So in this case, the index set is equal to 1. Okay, the index set is same. But the index set I can be arbitrary, can be finite. For example, 1, 2, 3, 4, 5. Okay, only 5 integers. Or maybe I into the R, the set of all real numbers, which is uncountably many, infinite. Okay, so. But anyway, the De Morgan law is very general in that case. Any questions? Okay, so now we will apply De Morgan's law to prove the proposition 2.2.b. If E1, E2 are events in sigma algebra F, then the intersection is also in F. Okay, because in the definition of a sigma algebra, for the third property, we just require that the union of this countably many events should be also in F, right? But the proposition shows that if we have countably many events in a sigma F, then their intersections is also in F. Okay, so the proof is here. Since En is in F, the En complement, okay, by 2, okay, by property 2, there, right? The complement there. All right, and then the union of the union is also in F by property 3, because the complement of En is in F, so we take the union. It's also in F by property 3. Okay, and then they imply that if we take but then the complement of this one is in F, again by property 2. So up to here, we use property 2 and 3 of a sigma algebra. Okay, now by De Morgan's law. Okay, so this is equal to, but what is that? This is the intersection of ENC of C by De Morgan's law. Okay, but what is that? The complement of complement again is equal to the EC itself. Okay, and this is equal to, okay, maybe I write here. Okay. Okay, so this is equal to the intersection. Okay, so this intersection is in F, and we prove the result. Okay, any questions? Any questions? Okay, so if no questions, then I stop here. And I will see you on Thursday.